Hello everyone and welcome back to AlexAeroLab. I hope everyone's doing great. The last few months have been pretty killer for me, but I'm super pumped to be back on this channel, working on it full time, and I'm excited to get going on these projects again. Because of this newfound freedom, there's some exciting changes coming to this channel. I'm going to be making some slight deviations from the original plan. I'll now be working on multiple projects in parallel, meaning I'll be uploading weekly and if not multiple times a week. Right now the focus is still going to be on the front wing project, but hopefully in a few weeks I'm also going to be incorporating some lap time simulation projects and some full-scale vehicle modeling. But let me update you on the state of the current project. In my previous video, I mentioned that I needed to perform a calibration study or modeling study first, but I didn't really present why I need to do this. In CFD and in any computational modeling, engineers are trying to replicate or predict reality. We create a model and solve equations in order to better understand a problem. However, at the end of the day, these are just models and may or not be replicating the real world. And that's why modeling studies are so important. We need to take existing experimental data and use that to validate our models to make sure they're predicting reality. And even in my relatively short career, I've seen too many engineers and scientists get lost in what I'm going to call the modeling sauce. In my previous employment, I've heard top scientists say they discovered new physics inside of a code. Like, really? We implemented unknown physics into a software? And in my graduate studies, I've heard people say, oh, we've trained this AI on this modeling data to better predict turbulence. It's like, no, you trained your AI model to better predict how you model turbulence. We just have to remember simulations are simulations, not reality. So with all that being said, let's get into the very first attempt at this modeling study. I was attempting to replicate the single element inverted wing and ground effect experiments performed by Jonathan Zarahan. I'll go into the finer details of this study in the final video on this project. But to summarize, Zarahan took a simple untwisted rectangular wing and tested how its performance changed as its proximity with the ground changed. The data was collected in the University of Southampton's 2.1 meter by 1.7 meter subsonic wind tunnel. To replicate this data, I created a CAD model of the wing tested in the experiments and simulated it in OpenFOAM 12 using Snappy Hex Mesh to create the domain. Now, an important part of CFD is ensuring that the mesh you're using is not impacting your results. And if you're unfamiliar with CFD, I think a good analogy is imagine you're doing a paint by numbers where originally the painting is just a grid of square boxes. If you have large boxes, you're not really going to be able to capture the level of detail you want. And therefore, you need to divide the paint by number boxes into smaller and smaller sections until eventually you'll reach a box size that gives you the desired level of detail you want. However, there's going to come a point where adding more boxes doesn't really add much more to it visually, and all you're really doing is spending more time filling out boxes. And that's really what we do in a CFD resolution study. We add enough resolution so that the desired level of accuracy is achieved, but not so much that it takes a bajillion million years for your computer to solve it. So that's exactly what I did. I created a baseline mesh and started dividing it into smaller and smaller sections until hopefully the lift and drag coefficients converged. Only they didn't. In fact, as the number of cells increased, there was really no pattern at all. And this came down to how I was modeling the boundary layers. These are areas surrounding the surface of a body in which the fluid flow is dominated by viscous effects. At the object surface, the fluid is moving at the same speed as the object. And if we're in a reference frame where we're moving with the object or the object is at rest, the surface velocity is going to be 0. And farther away from the surface, the flow will be moving at the free stream velocity. We can see this velocity distribution in this figure I took from Fluid Mechanics 101. This is an excellent channel if you want to learn more about CFD. In this image, we see the fluid velocity go from 0 to the free stream. Towards the bottom of this distribution, we see that it changes very rapidly. And again, back to that painting analogy. If we want to capture this large gradient, we're going to need smaller and smaller cells in this region. To accomplish this, we use inflation layers, like the ones pictured here. These are cells that start small at the surface and grow as you move away from the wall in the normal direction. Now, as some of you may know, Snappy Hex Mesh is notoriously bad at inflation layers. I really tried hard on this, and I really pushed all the mesh quality parameters to the maximum and tried many times to get something half decent to work. I was finally able to get something akin to real inflation layers. However, the maximum number of layers I could use without the whole mesh exploding was around 12. And this is not great, as really you need a minimum of like 20 to 25 cells to properly resolve anything. Another annoying feature you can't see in this image is that Snappy Hex Mesh builds the inflation layers by displacing the initial mesh as opposed to just replacing it. As a result, the ground boundary layer underneath the wing is always distorted and gives very poor results. Part of why I was struggling so much is that you need really small first cell layer heights in that inflation layer. Ideally, you would have them so small that you can resolve all the small eddies in the boundary layer, but this really isn't realistic, especially on my hardware. Instead, we use functions that approximate the physics at the wall. These are fit to experimental data and are called wall functions, and they're dependent on the non-dimensional length y+. And for the scope of this video, I won't go too much into detail on this, other than ideally you want your y+ to be less than 5. With my rather compromised mesh, I was achieving average y+ values on the surface of the wing of around 0.5. However, the reason my mesh convergence study was doing so poorly was my maximum y+ values were around 45 and occurring right at the suction side of the leading edge. And this is probably one of the worst places for this to be happening. I spent weeks working on this mesh, but unfortunately, the limitations just proved to be too much, and I knew I needed to pivot to a new meshing software. Unfortunately, also school was really ramping up at this time, and I knew I wasn't really going to be able to devote the time to fixing it right away. And so I decided to just run the modeling study anyway to see what type of results we'd get. And here are the results. On the left, we have the lift coefficient as a function of ride height, and on the right, we have the drag coefficient. The experimental values are shown in blue, and the simulation values in orange. And as you can see, there's some pretty bad comparison between the two. In the lift plot, it starts well, but as the proximity is reduced, it really doesn't match at all. It actually ends up resembling an experiment Zerahan performed where they tripped the boundary layer on the leading edge of the wing. However, the drag is nowhere near physical, and I don't even trust it enough to make any type of judgment on how close they are at the really low ride heights. So where does that leave us? Well, right now, the first project is actually going to become modeling this experiment. And then instead of doing this full study of 300 different simulations, what I'm going to do instead is what F1 teams do and design my own airfoil and test that using the same modeling choices I used to match this experimental data. So with that, stay tuned, thanks for watching, and I'm going to see you soon.